Okay, so today we're going to be talking about molecular models, and in that subcategory, Lewis dot structure, Vesper bonds, and then Vesper itself, or valence bonds rather. Okay, so to first you have to use the periodic table to calculate the total amount of electrons needed. So this is like a little table to help. And if it's a polyatomic ion, you just add the charge in. If it's a polyatomic cation, you subtract the charge. So once you have found the total amount of valence electrons needed, you'll just draw the skeleton structure. So you put the least electronegative atom in the center, which is usually um, the atom that comes first in the equation. Um, and then you just connect the remaining atoms with a single bond. So, remembering all that, you must distribute the remaining electrons to the surrounding atoms, keeping in mind the octet rule, which is you have to satisfy the octet rule by um, placing at least 8 electrons around each atom, with the exception of hydrogen, which only needs 2. So, if there are fewer than 8 electrons left over, you would just distribute them as double or triple bonds, which replace the single bond that is connecting the electronegative atom and the outer atom. So there are definitely special rules, of course. If it's an ion, you just place it in brackets and place the charge outside. And then with the exception to the octet rule, there are some molecules that have fewer than 8 valence electrons, which is usually group 2A or group 2 or group 2B. Um, so uh, if the some molecules have more than 8 valence electrons, so if that happens, you would just draw an extra atom and just connect it with usually a single bond, or you can just draw a lone pair or lone pairs of electrons. Here is a reference video. So an example of this is CCl4. So carbon is the least electronegative atom in this equation. So you put that in the center, and then you would write all 4 Cl's around it and connect each Cl to the carbon with a single bond. This one is pretty simple because each chlorine, it just needs 8 electrons. So 1, 2, 3, 4, 5, 6, and then the single bond counts as 2 electrons. So each atom fills out the octet rule. There's no lone pairs. There's no extra molecule added. However, COCl2, as you can see, there's a double bond, and so carbon goes in the middle because it's the least electronegative atom. And as we did on this side, Cl gets connected, and we all know chlorine only needs 8 valence electrons, so it's satisfied 1, 2, 3, 4, 5, 6, 7, 8. However, because oxygen over here, it's only 1 oxygen, not 2. You need to have a double bond to satisfy the octet rule for both oxygen and carbon. So we're going to talk about valence bonds a little bit later. So Vesper is valence shell pair electron repulsion, and this actually creates a molecular shape and predicts the shape of molecules in polyatomic ions, and it's all based on electrons to minimize the repulsion. And the domains of the electrons around a central atom, they place themselves in the most favorable bond angle, which is actually at its lowest energy state. So the energy states, remember, is like 1s, 3s, 3p, 4s, 4d, all that stuff. That's a whole nother section. So then we get to electron geometry, which we strive in Vesper for the ideal geometry, which is a central atom surrounded by all its bonds. with no lone pairs. So to create the VSEPR model, you would basically just follow the steps for the Lewis dot structure, and then you would determine the number of electron domains, and then you would just find the electron geometry. Pretty simple. Um, so definitely one of the rules of VSEPR is polar versus nonpolar, which gets a little tricky. So if there's no polar bonds, it's going to be nonpolar, obviously. If there's one polar bond, which is one dipole moment, it's going to be polar. If there are two or more dipole moments, everything's going to be based on shape, which I'll show you shapes a little bit later. If it's a symmetrical shape, and it's the ideal geometry, the dipole moments cancel each other out, so that means it's nonpolar. If it's a non-symmetrical shape, um, the dipole moments, they don't cancel each other out, so it becomes polar. So to show you a little bit about this, this one right here, the linear, is nonpolar because if you cut it in half, it's symmetrical. The same as the trigonal planar, if you cut it in half, it's still symmetrical. Just as the tetrahedral, if you cut it in half, it's still symmetrical. So to talk about valence bond theories, so valence bond theories, according to the theory itself, is when bonding takes place between atoms and their atomic and hybrid in their with their no when their atomic or hybrid orbitals interact or overlap. Um, so to interact, the orbitals must either be aligned along the axis or the orbitals must be parallel to each other, and perpendicular to the interatomic axis. So I hope that helped. Yeah.